are hearing me. Great. Is everyone hearing me? Okay. Okay. Thank you so much. Thank you for confirming that. I sincerely want to apologize for the delay in my lecture today. So today the focus is going to be on the lab session. And of course, give me 1 second. I'm going to share my lab slide. But before I share my slide, I would like to share, the canvas with you. The material that we actually want to use today is lab, let me see, that is lab 6, okay? It's right here. In fact, I've also uploaded lab 7, okay? So I'm going to click on that now. I'm going to download that for everyone to see. Okay, give me 1 second. I'm going to share that again. Okay, so this is the material for today. I need everyone to confirm if you're seeing the lab material now. This is a lab session. Can you confirm if you're seeing the lab? Okay, thank you so much. Thank you for confirming that. Okay, so we started this earlier in the week, time series analysis, of course, and I what we actually going to do in the lab today is to have a demonstration. Okay, I'm going to have a demonstration of how how you can demonstrate this in the lab. Okay, so that's exactly what I want to do today. But before I get started, I'm gonna say I'll first have a kind of recap on time series analysis. Okay, I remember I told you that time series analysis is actually situation where you are analyzing time series data, the data that you actually collected over time. Okay, you collected data set over time. That could be monthly, that could be weekly, that could be daily. An example of that is what we call a gas price. Okay, you could talk about the hospital admissions, okay, over time, and the reason why we're trying to analyze the data set is just for us to actually we want to investigate the trend. You get what I mean? So we want to investigate the trend. We want to look at the seasonality. We want to also want to see whether there's a kind of structural break, okay, and so on, like that. Okay, so and that is a okay. Just give me 1 second. Okay, I say I'm back again. Sorry about that. Can you confirm again if everyone is hearing me okay? Are you all hearing me okay? I need someone to confirm if you're still hearing me okay. Are you still hearing me? Okay, thank you so much. Okay, so what I was trying to say has to do with time series analysis. You know, the kind of analysis you conducted on time series data, you know, with an attempt to actually figure out the trend. And what I mean by the trend is whether there's going to be an upward movement or downward movement, or there's going to be some kind form of stability. Okay, so I gave an example of a gas price. You know, we live in a stochastic world, we live in a probability space, and there's a lot of variations. And of course, we actually want to have control on, you know, on our environment, and that is the reason why we need to conduct our analysis. So, well, one of the models that we have in time series is what we call the autoregressive model of order one. Okay, so you know, I walk you through in the class the autoregressive model of order one is a situation where you actually relate the current value of the series, okay, with the immediate past. Okay, for instance, if I want to talk, if YT represents the current gas price in United States, or you know, and the YT minus one, let's say this is a daily gas price. Of course, if this is the price of gas today, this is going to be the price of gas yesterday. Okay, so if the unit is monthly, then the YT is basically the price for this month, and the YT minus one, the price for last month. So with this model here is actually relating the current values of the series. You know, you're actually relating that against the immediate past. Now, looking at this model now, okay, you basically gonna see that we already have, we know what our C naught is. Our C naught equal to one minus one, and our C1 is actually 0.6. And of course, the WT, don't forget, I actually call that a noise. Okay, and of course, the specification here is that the WT noise actually follow normal distribution, which means zero and variance 0.01. Okay, so take a look at this model now. Okay, so looking at this model now, I think I've just explained to you, you know, how I explained this model to you the other time. You know, this is a arrow model of order one. You know, today in the lab, I'm actually going to walk you through how you can actually estimate parameters, okay, in your autoregressive model of order one. Okay, so I'm also going to walk you through how you can get, you know, the sample mean, the sample variance of that. You know, I walk you through the other time, the theoretical mean, the theoretical variance. And of course, you know, the theoretical mean, the theoretical variance, they're going to be different from the sample mean and sample variance. Okay. Now, this is going to be our task one today. You know what I want us to do? What I'm going to show you today, and I want you to get ready. Okay, you need to open your R Studio right now. We're going to make use of R software. So the very first task today, we actually want to simulate our data set. Okay, you want to simulate our data set, and our what is the sample size that we actually want to simulate is 2000. Take a look at that. And we actually assuming that our C1 is a 0.6, okay, and the standard deviation is a 0.1. You know why the standard deviation is a 0.1? Don't forget, if you, this is a model that we actually want to simulate the data from. Take a look at this. The C naught is -1, the C1 is a 0.6, and when you find the mean of this model here, okay, the mean of this model is -2.5. Don't forget the other time, if you want to find, I said you're going to use C naught, divided by 1 minus C1. So I hope you didn't forget that. Okay, so what I have here is a theoretical mean, and this is a theoretical variance, but you know what we want to do now. Okay, using this model now with the parameters that we have in it, with the expression for the variance of WT, we basically want to simulate data set, from which, the C0 and the C1 were actually computed. So that's exactly what I want to do here. So I believe you understand what I put here now. Okay, so this is the C1, and this is the standard deviation. Of course, we got this by finding the square root of the variance of WT, and of course, the 2.5 is actually the theoretical, the minus 2.5 is the theoretical mean. Okay, I think you understand the specification now. So what I'm gonna do now, I'm gonna copy this into R now, which I also want you to do the same. Okay, I'm gonna copy that now. Okay, when I copy that now, so I'm gonna stop my share. I'm actually gonna share my R studio, and I need everyone to confirm if you are actually seeing my R studio. Is everyone? I'm actually gonna walk you through how you can actually estimate parameters, okay, in your autoregressive model of order one. Okay, so I'm also going to walk you through how you can get, the sample mean, the sample variance of that. I walk you through the other time, the theoretical mean, the theoretical variance, and of course, the theoretical mean, the theoretical variance, they're going to be different from the sample mean and sample variance. Okay, now this is going to be our task one today. You know what I want us to do, what I'm going to show you today, and I want you to get ready. Okay, you need to open your R studio right now. We're going to make use of R software. So the very first task today, we actually want to simulate our data set. Okay, you want to simulate our data set, and what is the sample size that we actually want to simulate is 2000. Take a look at that. And we actually assuming that our C1 is 0.6, okay, and the standard deviation is 0.1. You know why the standard deviation is 0.1? Don't forget, this is a model that we actually want to simulate the data from. Take a look at this. The C0 is -1, the C1 is 0.6, and when you find the mean of this model here, okay, the mean of this model is -2.5. Don't forget the other time, if you want to find, I said you're going to use C0 divided by 1 minus C1. So I hope you didn't forget that. Okay, so what I have here is a theoretical mean, and this is a theoretical variance, but you know what we want to do now. Okay, using this model now with the parameters that we have in it, with the expression for the variance of WT, we basically want to simulate data set, from which, the C0 and the C1 were actually computed. So that's exactly what I want to do here. So I believe you understand what I put here now. Okay, so this is the C1, and this is the standard deviation. Of course, we got this by finding the square root of the variance of WT, and of course, the 2.5 is actually the theoretical, the minus 2.5 is the theoretical mean. Okay, I think you understand the specification now. So what I'm going to do now, I'm gonna copy this into R now, which I also want you to do the same. Okay, I'm gonna copy that now. Okay, when I copy that now, so I'm gonna stop my share. I'm actually gonna share my R studio, and I need everyone to confirm if you are actually seeing my R studio. Is everyone? if you see my house studio now, I need you to comment yes or you say yes. Okay, thank you so much for confirming that. So as I'm opening this house studio now, I also expect that you should also open your house studio. But just like what if you we want to simulate 2000 data set, okay, based on the parameters that I actually stated, okay, and you know what, you actually need to set seed, okay, set dot seed. You remember yesterday, right? You know the essence of setting seed, right? Because we actually want to simulate from population, and if you go into population several times, you simulate data set, you're basically going to have different values. And for us to be uniform, for us to get the same one, we can actually set a seed, okay, and put any number, but we got to put the same number. Okay, so then I'm going to paste the code now. Okay, take a look at that. It has taken it. Okay, if you actually want to see the force, because there's going to be 2000 data set, right? So if you want to see the force 6, you can just write add into y of t, then you run that. Oh my god, so take a look at that. Now if you're in your software, if in your R studio, if your home is displaying this now, I need you to say yes or you comment yes. If you have run this, if you've tried this now in your R software and this is what is displaying, I need you to say yes or you comment yes if it's actually working for you. Okay, so is there anyone that is not really getting that? Is there anyone? If you are not getting that, you pay for this service, you need to ask question and of course, comfortable going back, re-explaining. You get what I mean? Okay, if there's anyone who is not getting that. Okay, so what I'm trying to tell you now, I have 2000 observation. You know, they put in the head here. Okay, if I want to see the whole 2000, I can just write YT. And when I write YT, take a look at that. Okay, there's going to be a lot. Okay, now this is a data set, okay, that we actually generated. Okay, so the exercise one has already been achieved. Now the next thing that I actually want to do now is to probably make a plot. Okay, the other time in class, what I told you, right? In class, I actually talk about the use of time series graph, right? What do we use time series graph to do? Okay, you actually want to dictate if there's a trend or if there's a seasonality or if there's a structural break, okay, among other things. Okay, so I'm just going to do plot.ts into YT. Okay, then I'm going to plug that now. Okay, so give me 1 second. I'm actually going to share my screen now. Okay, I'm going to share my screen now. Okay, now we're going to post that. Okay, if you want to post that now, so you're going to see what is going to come up. So this is the time plot. Take a look at that. Okay, so that is a time plot based on the data set that I just generated. So take a look at that. Okay, so that is a time plot, that is a code now, right? Okay, I'm going to go back to the material. I'm going to go back to the material. So if that is not working for you, I need you to ask question. If it is not working, I'm actually going to go back and re-explain that. So in exercise 3, I want to find the sample mean and the variance for the data. Or what I'm just going to do is just to copy that. Okay, I copy that. Then you're going to go into R now. Okay, but I'll paste that now. Then you run that. Can you see that the mean is 8.013004? The variance is 1.076887. And if you take a look at the sample mean and the sample variance, they are not the same as the theoretical mean and the theoretical variance. But you know what? They're basically going to be very close. Okay, if that is not working for you, please let me know. If it is not working for you, let me know. Now, the next thing that I actually want to do now is to go into the ACF. Of course, you know why we actually consider the autocorrelation function. Okay, we consider autocorrelation function because that will tell us the type of model we're basically going to use within the class of time series modules. We have the autoregressive module of order 1, order 2, order 3, order 4, and so on like that. We have the moving average modules as well. Okay, so but the autocorrelation function will enable us to identify uh, whether the AR1 is appropriate for our data set. So the coding now is ACF, just going to write ACF. They're all going to be in a lowercase, right? So ACF into YT, if you copy that, okay, and you go into R now, okay, I'm going to copy, I'm going to paste that now into R. Okay, so what do I have? Take a look at that. You can see now. Okay, here, what you can see, because the fact that you know, uh, it is negative, you know, so give me 1 second. Let me see. Oh, okay. I think it should be this one. I'm gonna do that again so that you can actually. Okay, so I'm pressing that again, and I'm gonna run it now. Okay, take a look at that. So this is what I'm actually gonna have. As you can see here, as lag increases, the autocorrelation function is going down. Okay, the reason why it is going down for AR1 is because the C1 is positive. Okay, when the C1 is negative, it's basically going to be alternating between positive and negative. So this is an indication that probably autoregressive model of order 1 is basically going to work great. Okay, so if that is not working for you, I need you to ask me question. Is there anyone who want to ask me question? You know, I've walked you through exercise 1 to 4 now. So is there anyone who actually need clarification on what I've done so far? Is there anyone? So what you can see in the plot now is just that if the appropriate model is actually autoregressive model of order 1, okay, we expect the ACF plot, you know, we expect the autocorrelation function at different lag, okay, to decrease, okay, as, you know, to diminish to 0 as the lag increases. I just wanted to take note of that. Okay, so far so good, right? Okay, I'm gonna go to the next one. Okay, if you take a look at this guy, 0.6 raised to power k, that is a way to get the theoretical autocorrelation at lag k. Okay, the one I got here is just getting the plot. Okay, okay, just getting the plot, and of course you can also have a way to get the autocorrelation function at different lag. Now, what I want to do in exercise 6 is this. Okay, how do we fix autoregressive model of order 1? If I give you in exam, okay, you have some data set, you already have your data set, and I ask you to fit autoregressive model of order 1. So how are you going to do that in R? Okay, if you want to do that in R, like you're actually going to use this code that we call ARIMA. ARIMA is autoregressive integrated moving average model. Okay, so ARIMA 100 means I'm considering the AR1 integrated of order 0 and the moving average of order 0. Okay, so this means AR1. If I want to talk about AR2, it's going to be RMA 200. If I want to talk about AR3, it's going to be RMA 300. So what I'm going to do now, I'm going to copy this guy now. What am I looking for? I basically want to estimate the parameters in autoregressive model of order 1. Okay, I'm going to stop my share now. Okay, and I'm basically going to use this now. Okay, I'm going to paste that now. Take a look at that. I already have my YT, right? Okay, so what do I have? Take a look at that. This is my output now. If you try this and you don't get the output now, I need you to ask me question now. If you don't get that, I need you to ask me question if you don't get that. Okay, so you need to ask question if you don't get that. Okay, so this is what we have now. And I told you the other time, this guy now is your C1, but this guy here is not your C naught, but the estimate of the mu. Okay, this is the estimate of the C1. Okay, take a look at that. This is the estimated standard, or the sigma squared. That is a sigma squared W. That is the estimated one. Okay, this is the AIC. Okay, so take a look at that. Okay, so what I'm going to do now, I'm going to go back into the material now. Okay, I'm going to go back into the material now. Okay, so I just got this, so you can see that now. Okay, I told you this guy is not an intercept, it's actually mean, the minus 2.5 that you see here. This is a C1. Okay, the C1 here is more or less like the slope. Okay, and of course, the variance of the white noise is this guy, the one I call sigma squared W. Say variance of the white noise. So what if I ask you to run that on data set and I say, okay, what is the variance of the white noise? It is this guy here. I mean the estimated variance of the white noise. You know, the theoretical variance of the white noise is here. Let me show you let me give you the theoretical variance. Okay, look at that. The theoretical variance of the white noise is 0.01. But the estimated, the one you actually compute from the data set, okay, is actually this guy here. Is it not very close? It's very, very close. If you take this to 3 decimal, is the estimated variance of the, of the noise. It's actually close. It's more or less the same as the theoretical variance. Take a look at that. Okay, now you want to write, you know, the model out now. I said it's going to be y cap, okay, minus mu, right? Okay, equal C1 cap, okay, into yc minus 1 minus mu cap, right? So I think I've just plugged that in. The mu cap is basically this guy. You can see it's already here. Is a negative one. The C1, okay, is this guy here. That's why you put that here. And this is a mu. And I told you yesterday, you're actually going to simplify this model now. Okay, you're going to simplify that to arrive at this. Okay, when you simplify that, this is your final model. So right now, in your final model, this is your C naught, and this is your C1. So take note of that. Okay, in your final model now, your C naught is this guy, and your C1 is that. Is there anyone who need clarification on what I just done now? Is there anyone? Is there anyone who want to ask question, who need clarification? If you're good with my explanation now, if you really understand what I just demonstrated, I need you to say yes, or you comment yes. Okay, but if you're not getting it, do not hide your feelings. You need to ask me. Okay, so I want to go to the exercise number 7. Compare the fitted model to the theoretical model. Is the estimated slope of yt minus 1 close to the true value? 0.6 is the estimated variance of the white noise close to the true value. I told you the other time. Okay, the true value of C1 is this. The true value of the variance of the noise is this. And of course, with using the data set, I told you what we got as C1 and what we got at the estimated variance. Take a look at this. This is what we got as the estimated variance of the white noise. You're going to compare with the theoretical one. And this is what we got as the estimated, slope. Okay. And that is not far from the true one. Okay. That is just a question of, that they actually ask you. So take a look at that. Okay. So I'm going to go to exercise 8 now. Exercise 8 is talking about prediction. Just like before you can talk about prediction, we need to subject the model to diagnostic testing, which is basically going to be uh, looking into the autocorrelation function of residual. And we expect that the autocorrelation function of residual or at any lag should be within 0. Okay, but I want to assume that everything is good. How do I make a prediction? Okay, if my last data actually stopped in 2000, I can predict for 2001. Don't forget the final working model is this guy now, right? Okay, so I can make a prediction for this guy using the past value. Okay, so don't forget that we simulated 2000 data set, right? Okay, so I can use this model now to predict what the value for observation 2001 is going to be. Okay, so all what I'm just going to do is to plug in the value for Y 2000. Okay, then I'll be able to make a prediction about that. So that's exactly what I'm trying to say. So whatever the value is for Y 2000, you plug that in, multiply by this, then you simplify that. That will give you the predicted value for 2001. And if you want to do that in R, you know what I'm going to do, right? It's like predicting one ahead. This is ending 2000. You want to predict for 2001. That is one ahead. You can predict for 2 ahead as well. Yeah, you're going to say n ahead equal to 2. So if I copy this guy now, okay, that is the coding now. If I copy that, okay, and I paste that in R, okay, if I copy that now and I paste that, okay, don't forget my MOD is that right? Now it's actually giving me error. Oh, I do MOD. It's supposed to be MOD1. Okay, so I'm going to correct that. Okay, MOD1, because I named this as MOD1. Okay, so if I click on that, take a look at that. So that is a prediction now. Take a look at that. The prediction is actually this guy here. And this is the standard. The one here is the standard error associated with that prediction. So this is a prediction. The last value for 2000 is this guy. You see the last value in the data set for 2000, right? Is this guy. Okay. Let me see. Oh, it may not be that guy because Arrow did not display all the data set here. Okay, it may not be this guy. It may not, because this is 991, 992, 993, 994, 5, 6, 7, 8, 9. This is 1000. Arrow only display 1000. He omitted 1000. Don't forget. So the last one is not this guy. But automatically, when you write that code, okay, it's basically going to give you this. What if you want to predict 2 ahead? If you want to predict 2 ahead, that's what you're going to get. Okay. Okay. So is there anyone who need clarification on what I've done? Because that is all what I got for you today. Like I said, your exam will be posted on July 16 by 8 a.m. So check the announcement section and the syllabus. Okay, so this is what I got for you today. Is there anyone who need clarification? Is there anyone want to ask any question? If you are good with what I demonstrate, Yeah, the exam is tomorrow. You know, I'm gonna do this. I'm gonna show you the, I'm gonna show you the syllabus is already, I think I've said that before, in the syllabus. Give me 1 second. Exam is going to be posted July 16. Now, you look at the syllabus here. Earlier in the semester, I think that is already there. Look at, you're going to see now. See, I said the midterm two will be conducted between July 15 and this is a proposal. And when I was saying something here, now later said the exam will be posted on January 16 by 8 a.m. Look at that. And will be left open for 24 hours. I think you see that. So this has been in the syllabus. Okay, exam will be. So I was having between 15 and 16, but I later said it will be posted on July 16 by 8 a.m. So take a look at that. Also watch out for the for the final exam. Here I said it will be posted on July 29 by 8 a.m. So please take note of that. I'm using the syllabus and I'm not going to deviate from the syllabus. Okay, is there anyone who also need clarification on anything before I go today? Okay, so if everyone is good about my explanation today, I need you to say yes or you comment yes before I go. Are you okay with my explanation today? Oh my God, thank you so much for replying back. But if there's anyone who doesn't really understand, please do not hide your feelings. Okay, so make sure you stay safe and have a lovely weekend. Okay, bye for now, everyone. Yep, thank you.